We'll start in 1 minute. Today we'll continue in section 10 and chapter 11, and if there's time we might start section 11:11. We got to this problem yesterday. The directions are use known Maclaurin series to get Maclaurin series for the functions below. Okay, to get a Maclaurin series for this function, x squared times the natural log of 1 plus x to the third, we'll start by writing the Maclaurin series for the natural log of 1 plus x. So we found that one yesterday. So the natural log of 1 plus x it's an alternating series, x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, and so on. So in sigma notation, we can write it as n equals 1 to infinity, -1 to the n minus 1, and then x to the n over n. The next step, find the Maclaurin series for the natural log of 1 plus x to the third. To get this Maclaurin series, we just use the Maclaurin series for the natural log of 1 plus x and replace every x with x to the third. So replace every x with x to the third, we get x to the third minus x to the third to the second is x to the sixth over 2, and then plus x to the third is x to the ninth over 3, and so on. The next term is minus x to the 12th over 4. And then the sigma notation. All we have to do is replace the x with x to the third, so we get x to the 3n over n. Okay, so how do we get a Maclaurin series for x squared times the natural log of 1 plus x to the third? All we have to do is multiply both sides of this by x squared. So we just multiply the terms of the Maclaurin series up here, term by term, multiply each one by x to the second. So that isn't too hard. We'll get x to the 5th minus x to the 8th over 2 plus x to the 11th over 3 minus x to the 14th over 4, and so on. And then in sigma notation, we just multiply x to the 3n times x to the 2nd. And then using properties of exponents, we can write this as x to the 3n plus 2 over n. So that's all there is to that. All right, the next page. Find the Taylor series for f of x centered at the given value of a. So for this function, f of x equals the natural log of x, and a is equal to 2. So let's remind ourselves of the Taylor coefficients. The form that they take, C sub n, is the nth derivative of f evaluated at a divided by n factorial. Okay, so now it's just algebra and arithmetic and applying the derivative formulas. So f of a, f of 2 is just the natural log of 2. So let's find the first few derivatives, and then afterwards we'll evaluate them at x equals 2. If f of x is the natural log of x, then the first derivative is 1 over x. The second derivative is negative 1 over x squared. The third derivative, this will be positive 2 over x to the 3rd. And let's do a couple more. The fourth derivative, this is going to be negative 6 over x to the 4th. And then the fifth derivative, this will be positive 24 over x to the 5th. But notice, so starting with the second derivative, we have the negative of 1 factorial over x squared. For the third derivative, we have 2 factorial over x to the 3rd. In the fourth derivative, we have negative 3 factorial over x to the 4th. For the fifth derivative, in the numerator, we have 4 factorial over x to the 5th. Just an observation that can be useful. Then we want to know what each of those is when we evaluate it at a equals 2. So the first derivative evaluated at 2 is 1/2. Second derivative evaluated at 2 I'm going to write it as minus 1 over 2 to the second, even though we know what that is. The third derivative, evaluated at 2. I mean, this is 2 over 2 to the second, 2 to the third. The fourth derivative, evaluated at 2, is negative 6 over 2 to the fourth. And then the fifth derivative, evaluated at 2, is 24 over 2 to the fifth. Okay, so now let's write the Taylor series. The first term is f of 2. The next term is the first derivative evaluated at 2 divided by 1 factorial. So I'm going to write this as 1 over 2 times 1 factorial. And then we have times x minus 2. Then the next term, well, it's negative, so we'll write minus 1 over 2 to the second times 2 factorial times x minus 2 to the second. Then the next term, so let's write this as 2 over 2 to the third, and then 3 factorial times x minus 2 to the third. Okay, a couple more if we can squeeze them in. The next term is negative, so negative 6 over 2 to the fourth times 4 factorial. And then the next one, 24 over 2 to the fifth, and then times 5 factorial. I am sorry, I missed the x minus 2 to the fourth. And then this one is x minus 2 to the fifth, and so on. Okay, let's simplify this a little bit. F of 2 is the natural log of 2. So the natural log of 2 and plus 1 over 2 times 1 factorial times x minus 2 to the first minus 1 over 2 to the second times 2 factorial is just 2. And then x minus 2 to the second. Okay, notice on the next one, 2 divided by 3 factorial simplifies to 1 over 3. So we can write this as 1 over 2 to the third times 3 times x minus 2 to the third. So we have room for one more term, but we'll be able to see the pattern. we have minus 6 over 2 to the 4th times 4 factorial. But 6 divided by 4 factorial is 1 over 4. So we have minus 1 over 2 to the 4th times 4 times x minus 2 to the 4th, and so on. Okay, so we can write the sigma notation. The first term is the natural log of 2. And then in sigma notation, I think we'll start with n equals 1. I can always change my mind later. Yeah, so this will be 1 over 2 to the n times n. It is alternating, so in the numerator I'll put negative 1 to the n minus 1, and then x minus 2 to the n. Okay, I was kind of sloppy, but I think you get the idea. Okay, let's move on to the next one. Find the Taylor series for f of x equals e to the 2x, and a is equal to 3. First, let's compute the first few derivatives. The first derivative of e to the 2x is 2 times e to the 2x. The second derivative is 2 times 2. I'll write 2 to the second times e to the 2x. The third derivative is 2 to the third times e to the 2x. The fourth derivative is 2 to the fourth times e to the 2x, and so on. And then each of these evaluated at a equals 3. So f of 3 is just e to the 6th. Then the first derivative evaluated at 3 is 2 times e to the 6th. The second derivative evaluated at 3 is 2 to the second times e to the 6th. The third derivative evaluated at 3 is 2 to the third times e to the 6th. Then the fourth derivative evaluated at 3 is 2 to the fourth times e to the 6th. Okay, so now we can write down the Taylor series. The first term is f of 3, or e to the 6th. And then plus the first derivative evaluated at 3 divided by 1 factorial times x minus 3 to the first. So we'll write this as 2 times e to the 6th over 1 factorial times x minus 3 to the first. Then the next term in the numerator, we have 2 to the second times e to the sixth divided by 2 factorial times x minus 3 to the second. So you can see the pattern emerge. The next term, 2 to the third times e to the sixth over 3 factorial times x minus 3 to the third. And then one more term, we have 2 to the fourth times e to the sixth over 4 factorial times x minus 3 to the fourth, and so on. So in sigma notation, we'll start at n equals 0. And we have 2 to the n over n factorial times e to the sixth times x minus 3 to the n. Yep, I think that works. Okay, at the next page, use the Maclaurin series for e to the x to get a Maclaurin series for e to the negative x squared. So a reminder of what e to the x is, the Maclaurin series for e to the x. This is 1 plus x over 1 factorial plus x squared over 2 factorial, and so on. So the sigma notation. To get a Maclaurin series for e to the negative x squared, we just replace every x in the Maclaurin series for e to the x with negative x squared. So we'll get 1 plus negative x squared to the first over 1 factorial plus negative x squared to the second over 2 factorial plus negative x squared to the third over 3 factorial. I'll put in one more, negative x squared to the fourth over 4 factorial, and so on. Okay, then in the next line, so the term negative x to the second to the first is negative x to the second. So we have minus x to the second over 2 factorial. And the next term, when we square negative x squared, we get positive x to the fourth. So this will be plus x to the fourth over 2 factorial. This one should be 1 factorial. Okay, the next one, when we raise the term negative x to the second to the third, we get minus x to the sixth, and then over 3 factorial, and then plus x to the eighth over 4 factorial. But we can see the pattern. It's an alternating series. So if we start at n equals 0, we have negative 1 to the n. And the terms are x to the 2n over n factorial. Okay, that looks right. This is what we get for e to the negative x squared. Then let's evaluate the antiderivative of e to the negative x squared by using the Maclaurin series for e to the negative x squared. Okay, so term by term, we just write down antiderivatives for the terms in the Maclaurin series for e to the negative x squared. So an antiderivative for 1 is x. And then we have minus x to the third. I'll write this as over 3 times 1 factorial. And then plus x to the fifth over 5 times 2 factorial. And then minus x to the 7th over 7 times 3 factorial. And the next term, x to the 9th over 9 times 4 factorial. So what do we get in sigma notation? Well, if we start at n equals 0, it's an alternating series. I'll rewrite it down here where I have a little bit more room. So if we start at n equals 0, then we have negative 1 to the n. So I need x to the 2n plus 1, it looks like. And then divided by uh, 2n plus 1 times n factorial. Zero factorial is 1, so this looks like what we want. So when you see a problem like this on the final, don't spend a lot of time trying to find sigma notation. If you can find 5 or 6 terms in the infinite series, that will be pretty much all you need to be able to do. Hey, do you remember earlier this semester, if you read it in the book, I think I mentioned it in class, that there isn't a known antiderivative of e to the negative x squared involving simple functions. And so being able to express e to the negative x squared as a power series or a Taylor series, then we can evaluate the derivative term by term. Okay, the next one is the definite integral of e to the negative x squared dx from 0 to 1. So when x is 0, all of the terms will be 0. So all we have to do is replace every x with 1 in the infinite series. So this will be equal to 1 minus 1 over 3 times 1 factorial plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial, and so on. But we can simplify some of those fractions. So 1 minus 1/3 plus 1/10. 3 factorial is 6, so minus 1 over 42. And let's see, 4 factorial is 24. 9 times 24 is 216, so plus 1 over 216, and so on. All right, now we'll move on to section 11.11. This is the section on Taylor polynomial applications. So the first paragraph, as we have seen, many functions are equal to the sums of their Taylor series or Maclaurin series, and therefore those functions can be approximated by their Taylor polynomials. And according to the author of the textbook, Taylor polynomials are used in computer science because polynomial functions are the simplest of functions. And they are also used in physics and engineering. And to quote the textbook, in particular, Taylor polynomials are used in relativity, optics, black body radiation, electric dipoles, the velocity of water waves, and the building of highways across a desert. All right, the next part, if f of x is equal to the sum of its Taylor series at A, then as we have seen, f of x is equal to this infinite series. The coefficients of the Taylor series are the nth derivative of f evaluated at A divided by n factorial. And those are multiplied by the binomial x minus a to the power n. So if f of x is equal to the sum of its Taylor series at A, then the function can be approximated by a Taylor polynomial, which is just t sub n of x is just a polynomial of degree n. And we've seen this notation before for the nth degree Taylor polynomial. Okay, so the idea here is if f of x is equal to the sum of its Taylor series at A, in other words, since f of x is equal to the limit of the Taylor polynomials as n goes to infinity, it follows that f of x can be approximated by an nth degree Taylor polynomial. The larger the n, the better the approximation. So here's a little exercise. Suppose a function f is equal to the sum of its Taylor series at a. Find the first degree Taylor polynomial of f at a, and then look at it and see if it looks familiar. So I'll give you something to do for 3 or 4 minutes. Just using the notation for a Taylor series of a function f, find the first degree Taylor polynomial of f at a. So in other words, find t sub 1 of x. And when you find it, you should be able to type it in. Do you have an answer? We can use the formula for t sub n of x. So t sub 1 of x, the first term is just the function evaluated at a. So the first term is f of a. And then we add that to the second term, which is the first derivative evaluated at a. I'll just write f prime of a divided by 1 factorial, so I won't bother to write it. So it's just f prime of a multiplied by the binomial x minus a. Okay, that's the answer. That's the first degree Taylor polynomial of f at a. So what is that equation? All right, suppose we have the graph of some function y equals f of x, and we pick a point on the graph. Let's suppose the x-coordinate of that point is a, and the y-coordinate then is f of a. From Calculus 1, do you remember how to find the equation of the tangent line that passes through that point? So that's the tangent line. So how do we find the equation for that tangent line in symbols? So in order to find an equation of a straight line in the xy plane, if we have knowledge of just two things, we can write the equation for that straight line. Well, if we know the x and y coordinates of a point on the line, that's one of the things that we can use. And the other is if we know the slope of that line. So knowing the slope and the x and y coordinates of one point, that's enough to find the equation for that line. All right, so what is the slope of that line that passes through the point A, f of A, on the graph of y equals f of x? So the slope is often represented by lowercase m, but if the function y equals f of x is differentiable, meaning that the derivative exists, then the slope of the line that passes through A, f of A, is f prime of A. All right, so what can we do next? We have the slope of the line, f prime of A, and we have a point on the line. So we can start by using the point slope form for a straight line. The point slope form can be used if we know the slope and the x and y coordinates of a point on the line. Then the point slope form is y minus y1 equals m times the quantity x minus x1. Okay, so we'll do that with this point, a f of a, and the slope f prime of a. So using the point slope form, we can write y minus f of a, that's the y minus y1, equal to the slope f prime of a times x minus a. And so this is one way to write the equation of the tangent line, but if you just solve it for y, we can write it as y equals f of a plus f prime of a times x minus a. Okay, but this is exactly what the first degree Taylor polynomial of f at a is. So the first degree Taylor polynomial of f at a is the equation, or is the tangent line equation that passes through the point a, f of a. So one more thing before we move on. Do you remember what a tangent line is used for? If we have an equation for a tangent line. Well, we know that Taylor polynomials, from what we read earlier, Taylor polynomials can be used to approximate the function f. So the same with the tangent line. We use a tangent line to approximate function values for values of x near a. So I'll try to squeeze that in here. We use t sub 1 of x, that's just the tangent line, to approximate the function f at x values near a. That's one of the uses of the tangent line. Okay, let's start the next part. So on this one, let f of x be equal to the natural log of x. Find t sub n of x, the nth Taylor polynomial of f at a equals 1. Then use the degree, or the sixth degree Taylor polynomial of x at a equals 1 to approximate the natural log of 1.5. So let's just work on finding the sixth degree Taylor polynomial. So that means we're going to have to find six derivatives. So if f of x is the natural log of x, then the first derivative is 1 over x. The second derivative is negative 1 over x squared. The third derivative is positive 2 over x to the third. The fourth derivative is negative 6 over x to the fourth. The fifth derivative is positive 24 over x to the fifth. And then finally, the sixth derivative is negative 120 over x to the sixth. Okay, so let's write down in symbols what this Taylor polynomial of degree 6 is. So in symbols, it's f of a plus the first derivative evaluated at a divided by 1 factorial times x minus a. plus the second derivative evaluated at a divided by 2 factorial times x minus a to the second. Then the third derivative evaluated at a divided by 3 factorial times x minus a to the third. The fourth derivative evaluated at a over 4 factorial times x minus a to the fourth. Then the fifth derivative evaluated at a divided by 5 factorial times x minus a to the fifth. And I'll just write down the last term and then we'll be done for today. The sixth derivative evaluated at a divided by 6 factorial times x minus a to the sixth. Okay, on Friday we'll finish these problems and probably look at some more. So go ahead and sign in for attendance.